Okay, so we're going to continue our discussion of counting and probability with R combinations and with repetition allowed. All right, so in this section we ask, how many ways are there to choose R elements without regard to the order from a set of n elements if repetition is allowed? A good way to imagine this is to visualize the n elements as categories of objects from which multiple selections may be made. Definition and notation. An R combination with repetition allowed, or a multiset of size R, chosen from a set X of n elements, is an unordered selection of elements taken from X with repetition allowed. If the set X contains little x1, little x2, etc., we write an R combination with repetition allowed, or multiset of size R, as the x1, x2, etc. to xi in square brackets, where each xi sub I sub j is in X, and some of the x sub I sub j may equal each other. So the set is defined using the curly braces, and the multiset of size R is square brackets. So make sure you remember that distinction. Write a complete list of the following numbers of 3 combinations with repetition allowed, or multisets of size 3 that can be selected from 1, 2, 3, and 4. Observe that because the order in which the elements are chosen does not matter, the elements of each selection may be written in increasing order, and writing the elements in increasing order will ensure that no combinations are overlooked. So, to do that, you'd see all combinations with 1 that start with 1, 1. All combinations that start with 1, 2. All the combinations that start with 1, 3, or 1. And all combinations that start with 2, 2. And so on and so forth. So there are 23 combinations with repetition allowed. The number of R combinations with repetition allowed, or multisets of size R, that can be selected from a set of n elements, is R plus n minus 1, choose R. This equals the number of ways R objects can be selected from n categories of objects with repetition allowed. So, a person giving a party wants to set out 15 assorted cans of soft drinks for his guests. He shops at a store that sells 5 different types of soft drinks. How many different selections of cans of 15 soft drinks can he make? If root beer is one of the types of soft drinks, how many different selections include at least 6 cans of root beer? If the store has only 5 cans of root beer, but at least 15 cans of each other type of soft drink, how many different selections are there? A little bit more complicated in the counting category here. Well, with A, think of the 5 different types of soft drinks as the N categories, with and the 15 cans of soft drinks to be chosen as the R objects. So N equals 5 and R equals 15. Each selection of cans of soft drinks is represented by a string of 5 minus 1, or 4 vertical bars to separate the categories of soft drinks, and 15 crosses to represent the cans selected. So this string here represents a selection of 3 cans of soft drinks of type 1, 7 of type 2, none of type 3, 3 of type 4, and 2 of type 5. The total number of selections of 15 cans of soft drinks of the 5 types is the number of strings of 19 symbols, 4 of them being the vertical bar and 15 of the x's, is equal to 15 plus 5 minus 1, choose 15. So work that out, it's 19 factorial. Divided by 15 factorial times 19 minus 15 factorial, or 19 choose 15. So 19 factorial divided by 15 factorial times 19 minus 15 factorial is equal to 3,876. Quite a bit of quite a bit of number of possibilities for the number of combinations of soft drinks. If at least 6 cans of root beer are to be included in the selection, you can imagine choosing 6 such cans first, and then choosing 9 additional cans. The choice of the 9 additional cans can be represented as a string of 9 X's and 4 vertical bars. For example, if root beer is type 1, then the string here represents a selection of 3 cans of root beer, in addition to the 6 cans initially chosen. None of type 2, 2 of type 3, 4 of type 4, and none of type 5. So, the number of selections of 15 cans of soft drinks of the 5 types, including at least 6 cans of root beer, is the number of strings of 13 symbols, 4 being the vertical bar and 9 of them being the X's. So you would have 9 plus 4, choose 9, or 13 factorial over 9 factorial times 13 minus 9 factorial, which is 715 different ways you can select the sodas. If the store has only 5 cans of root beer, then the number of different selections of 15 cans of soft drinks of the 5 types is the same as the number of different selections that contain 5 or fewer cans of root beer. So let T be the set of all possible selections, assuming that there are at least 15 cans of each type. Let R sub less than or equal to 5 be the set of selections from T that contain 5 or fewer cans of root beer. And let R greater than or equal to 6 be the set of selections from T that contain 6 or more cans of root beer. So the total is the union of these two sets, and the intersection has to be 0, or the empty set. By part A, the total number of selections possible is 3,876, and by part B, n greater than or equal to 6 is 715. Thus, by the difference rule, there are 3,161 different combinations with for the set of R less than or equal to 5. So when there are only 5 or fewer cans of root beer, the number of different selections of soft drinks is 3,161. If n is a positive integer, how many triples of integers from 1 through n can be formed in which the elements of the triple are written in increasing order, but are not necessarily distinct? In other words, how many triples of integers I, j, and k are there in with 1 being less than or equal to I, which is less than or equal to j, less than or equal to k, less than or equal to n. Any triples of integers with those conditions can be represented as a string of n minus 1 vertical bars and 3 crosses, with the positions of the crosses indicating which 3 integers from 1 to n are included in the triple. So this is for n equals 5. And how many triples can be done for that? Thus, the number of such triples is the same number as strings of n-1 vertical bars and 3 x's, which is 3 plus n-1, choose 3, or n plus 2, choose 3, which is n times n plus 1 times n plus 2 all over 6. So, yeah. How many solutions are there to the equation x plus 1 plus x sub 1 plus x sub 2 plus x sub 3 plus x sub 4 equals 10 if those variables are non-negative integers? Well, think of the number 10 as divided into 10 individual units, and the variables given are as 4 categories into which these units are placed. The number of units in each category indicates the value of x sub I in a solution of the equation. Each solution can then be represented by a string of 3 vertical bars to separate the 4 categories and 10 crosses to represent the 10 individual units. For example, in the following table, the 2 crosses under the x1, 5 under x2, and 3 crosses under x4 represent a solution equal to x sub 1 equals 2, x sub 2 equals 5, x sub 3 equals 0, and x sub 4 equals 3. So you get 2 plus 5 plus 0 plus 3, which is 10. So therefore, there are as many solutions to the equation as there are strings of 10 crosses and 3 vertical bars, namely 13 choose 10, or 13 factorial times 10 factorial, or divided by 10 factorial times 13 minus 10 for a factorial. Which equals 286 different strings. Remark, deciding which formula to use. Always an important thing. Earlier we discussed 4 different ways of choosing k for elements from n. The order in which the choices are made may or may not matter, and the repetition may or may not be allowed. The following table summarizes which formula to use in which situation. If order matters and repetition is allowed, then it's n to the k. If order does not matter, then k plus n minus 1, choose k. And then repetition is not allowed. It's the number of permutations of n in k. And if order does not matter, then it's n choose k. So those are the 4 formulas that we discussed and the situations in which they should be used. And that's it for that slide deck. And section 7 of counting and probability is Pascal's formula and the binomial theorem. And you thought you got away from the binomial theorem in Algebra 2. Not quite. In this section, we derive several formulas for the values of n choose r. The most important is Pascal's formula, which is the basis for Pascal's triangle and is a crucial component of one of the proofs of the binomial theorem. We offer 2 distinct proofs for both Pascal's formula and the binomial theorem. One is called the algebraic because it relies to a great extent on algebraic manipulation. And the other is called combinatorial because it is based on the kind of counting arguments we have been discussing in this chapter. Pascal's formula. Pascal's formula, named after the 17th century French mathematician, is one of the most famous and useful in combinatorics, which is a formal term for the study of counting and listing problems. It relates the value of n plus 1 choose r to the values of n choose r minus 1 and n choose r. Specifically, it says that n plus 1 choose r equals n choose r minus 1 plus n choose r, whenever n and r are positive integers and r is less than or equal to n. This formula makes it easy for it to compute higher combinations in terms of lower values. The slide got screwed up, so reading it is kind of challenging. It probably presents better in PowerPoint. It's kind of muddled here. Yeah, I'll look at this better here, more graphically. It might be a little bit clearer anyway. Pascal's triangle, shown in Table 971, is a geometric version of Pascal's formula, where sometimes it's simply called the arithmetic triangle because it was used for centuries before Pascal by Chinese and Persian mathematicians. But Pascal discovered it independently, and ever since 1654, when he published a treatise that explored many of its features, it has generally been known as Pascal's triangle. What are the values of 6 choose 2 and 6 choose 3? Well, by construction, the value in row n of column R and column R of Pascal's triangle is the value of n choose r for every pair of positive integers n and r, with r being less than or equal to n. By Pascal's formula, n plus 1 choose r can be computed by adding together n choose r minus 1 and n choose r, which are located directly above and left of n plus 1 choose r. Thus, 6 choose 2 is 5 choose 1 plus 5 choose 2. And 6 choose 3 is 5 choose 2 plus 5 choose 3, or 15 and 20 respectively. So, Pascal's formula, theorem 971, n plus 1 choose r equals n choose r minus 1 plus n choose r. Use Pascal's formula to derive a formula for n plus 2 choose r in terms of values of n choose r minus 1, and n choose r minus 2. Assume n and r are non-negative integers and 2 is less than or equal to r, which is less than or equal to n. Well, by Pascal's formula, n plus 2 choose r is n plus 1 choose r minus 1 plus n plus 1 choose r. Now apply Pascal's formula to n plus 1 choose r minus 1 and n plus 1 choose r, and substitute into the above to obtain this monstrosity. But it's simple substitution, so you can get the n choose r minus 2 plus 2 times n choose r minus 1 plus n choose r. Yeah. For all non-negatives n and r, such that 2 is less than r, which is less than or equal to n. Now the binomial theorem. In algebra, a sum of two terms, such as a and b, is called a binomial. The binomial theorem gives an expression for the powers of binomials for each a plus b raised to the n for each non-negative integer n and all real numbers a and b. The binomial theorem is given here. The sum of n, the summation of from k from 0 to n choose k times times a to the n minus k times b to the k. So you multiply it out, and the terms of the various powers, or various terms of it, are calculated using the n choose 1 to n choose n choose n minus 1. Note that the second expression equals the first because n choose 0 is equal to 1 and n choose n is 1 for all non-negative integers n, since b to the power of 0 is 1 and a to the n minus 1, n minus n is 1 as well. So for any real number a and any non-negative integer n, the non-negative integer powers of a are as follows. A to the n equals 1 if n equals 0, and a times n minus 1 if n is greater than 0. It's a recursive definition there. Expand the following expressions using the binomial theorem. Yeah? A plus b raised to the fifth. Go through all these calculations, and you get a to the fifth plus 5a to the fourth b plus 10a to the third b to the second plus 10a to the second b to the third plus 5a b to the fourth plus b to the fifth. So if you recognize a pattern there, your powers of a decrement to 0, powers of b increment to, from 0 to 5, and the factor matches the power of the initial equation. Choose 1, 2, 3, 4, etc. So same situation going on here. Express the following sum in closed form without using a summation symbol and without using an ellipsis. Summation of k from 0 to n choose k, 9 to the kth power. Well, when the number 1 is raised to any power, the result is still 1. So it's 1 plus 1, or 1 plus 9. Yeah, 1 to the n minus k times n 9 to the k, which is by the binomial theorem going the other way, is 1 plus 9 to the n, or 10n. So that's a part of algebra that I never was very good at, coming up with terms to add to existing equations to simplify things. Looking at this, it's not obvious. Oh, add 1 to the n minus k. Who comes up with that? That's a level of mathematical creativity that I just never inherited, I guess. I don't know. But anyway, that'll be it for this slide deck. And that'll be it for the day. Let's see here. No class on Thursday. Our final lecture will be next Tuesday, and then there will be no class on the following not this Thursday, but next Thursday. And then it will be finals week. I looked up the final schedule of this class. I believe is Tuesday at 1 or 2. I don't remember. Oh, well, it's on my phone. But it'll be around class time on Tuesday or Thursday. The other class is going to be the other one. So I'll get it straight and put an announcement out there. Or actually, I think I might have already done that. Put an announcement out there on Canvas saying if you missed a quiz or exam, time is short on making those up. And the final exam is, it's not there? Thought I did it last week. Let's see here. Yeah, April 10th, final exam announcement. Yeah, final exam is Tuesday, April 28th from 1 to 2:50. Yeah, many missing assignments or examinations. You are required to make up those before close of business on the 24th. No exceptions will be made. Have 2 weeks, now less than that, 10 days to get them in. So, yeah, Tuesday 1 to 3-ish on finals week. If you are from out of town and need to leave on finals week before the final, let me know. I have the final already written up. We can get you taking the final before finals week. But otherwise, it'll be on Tuesday the 28th. So if anybody here from out of town that's leaving finals week? No? Okay, I guess we'll see everybody on the 28th. But yeah, no class this Thursday. Class on Tuesday. We'll wrap up chapter 9. Oh, also, don't forget, I don't remember what the due date is on it, but chapters 6 and 7, the extra credits. I don't know if very many people have done those yet. Those can substitute quiz and test grades if you do those chapters, homeworks. Do on the 30th? Okay. So get those done if you need the extra credit, or if you just want to learn more about sets and functions. But anyway, okay, have a good day. See you on Tuesday.